So let's now look at some properties of a minimal spanning tree, okay? But first, let me give some motivation. As I already mentioned, okay, a spanning tree, a tree essentially is the minimal number of edges that you need in order to connect a set of nodes, okay? Now imagine that I give you this graph, which is weighted, where let's say that this is the cost of building a road segment between two houses, okay? Now I ask that, okay, I want to connect all the houses, but I only want to do so with the minimum possible way at the costs, okay? What does that mean? I essentially need to find a way to span to reach all the houses, but whose total cost has to be smaller. In other words, we're looking for a minimal spanning tree for this graph, okay? And turned out that for this one, the dark colored, the black edges form a minimal spanning tree, and the total cost is smallest possible, okay? All right. So the minimal spanning tree problem in general is that we're given a weighted undirected graph. So note that again, here the weight can be positive or negative, okay? And the output is that we want to compute the minimal spanning tree with the smallest, we want to compute a spanning tree with the smallest total weight. And the way that we're going to represent that is that if I give you the edges of a minimal spanning tree, then the collection of them is sufficient to describe the tree. Okay, so we just want to output the set of edges in the tree. Okay. Okay, so in this case, if I give you the underlying graph, then you should return all the the shaded edges. Okay. Okay, so before we talk about the algorithm to achieve that, let's first look at some properties of a minimal spanning tree. Here's a very important property. Okay. And we're going to use this property essentially to design a greedy algorithm to compute minimal spanning tree. Okay, so this is a very important, a key property of minimal spanning tree. Pretty much all the algorithms to compute minimal spanning tree kind of leverage this property. Okay, so what is it saying? It said that suppose you already give me. So let's say this is a minimal spanning tree of your graph. Let's say your graph has edges. This is your graph. Okay, and the blue is a minimal spanning tree of the graph. Okay, the green are all the other edges. Okay, so some edges, like this green one, is not in the minimal spanning tree. Okay, then you can ask, why wasn't this green edge selected to be in the minimal spanning tree? Okay, it turned out that take any edge which is not in the minimal spanning tree. Okay, then the following must hold. What is it? Remember that since this green edge is not in the minimal spanning tree, when I added it to the together with the blue tree edges, there must be a unique cycle that it forms, right? So in this case, the unique cycle is that this is unique path between UV and together with this green edge. Okay, then the property is that in this cycle, C, okay, E must have maximum largest weight, edge weight. Okay, intuitively, that's why I didn't want to E, because the edge weight is too large. I have ways to connecting this nodes with a shorter, less expensive edges. Okay, so adding any edge to the tree, then the form a cycle. And the reason that edge was not chosen was because that if you look at this unique cycle it formed, this edge actually has the largest weight among all the edges in the cycle. Okay, so here's a better example. So now this is the input graph, and the shaded color is shaded edges give us a minimal spanning tree. Okay, now pick any non-tree edge. Okay, let's say that I pick this one. Okay, this edge, because I have a spanning tree, so when I added this edge, E, I form a unique cycle. This is a unique cycle we formed together with the tree. Okay, E and the tree form a unique cycle. And we can verify E has weight 11, but all the other edges here all have weights at most 11. So E has the largest weight. Okay, you can verify again with this. Let's say we can also take this edge. If this one is an edge E. Then when I add it, I form this cycle. Okay, in this case, this edge still has the largest weight, although the another edge has the same weight as this one, but still this one has the largest weight. Okay, so in other words, any non-tree edge, okay, well, when you add it, form a cycle, and that non-tree edge actually has the largest weight among all the edges in the cycle. Okay, so why is this the case? Why does this property hold? Okay, so here's the intuition. So intuitively, let's say that I add an edge E, and let's say that this one, that the weight was not 11. Let's say the weight was only 7. Okay, so in other words, now I look at this cycle that it formed. This was not the largest weight. Okay, if that's the case, then I could, there must be another edge which has a larger weight. So in this case, this edge 8 has weight 8, the edge DG, which is bigger than the edge IH. Okay, then what I could do is that I could simply remove this edge from my spanning tree and instead add this one in. Okay, then I replace this edge DG with the edge HI. And intuitively, I still have a spanning tree because I'm still connecting all the nodes and there's no cycle. Okay. However, now I reduced the weight. So that's not possible. So you cannot find another edge with bigger weight in the cycle formed by E under this tree. Okay, so this is intuitively why this is the case. Now I wrote the argument here of the proof. You just need to understand the intuition. Okay, so the proof is rather short here. Okay, so basically, if E does not have the largest weight in this cycle C, then there's another edge has bigger weight. Okay, then what I could do is that I can take this other edge away from my current tree and then replace it by E. And this is also spanning tree of G, and the weight is getting smaller. This new tree has smaller weight. So the original one cannot be minimal. So that's a contradiction, which means that the assumption is not right. E must have the largest weight in C. Okay, so that's the idea. All right, questions? Okay, so with this property, now I want to talk about an algorithm for the minimal spanning tree. Okay. Okay. So here's the problem. We're given a weighted undirected graph, and we want to compute all the edges in the minimal spanning tree. Okay. It turned out that, as we already mentioned, a minimal spanning tree first is a spanning tree, namely it consists of v minus 1 number of edges that connect all nodes with no cycle. Okay, and it also should have the smallest cost. Okay, it turned out that most algorithms compute a minimal spanning tree intuitively are all going to grow the tree edge by edge. It's just going to add more and more edges, making sure that there's no cycle through the way. And at any stage, it makes sure that it chooses a safe edge greedily, in the sense that by adding this edge, the new subset of edges still form a partial minimal spanning tree. Okay, so the difference in all this algorithm depends on how we're going to choose the safe edge. Okay, in particular, to make this idea more concrete, we're going to introduce 2 algorithms. Okay, one is called the Prim's algorithm. Let me actually first say Prim's algorithm. One is called the Kraskov's algorithm. Okay, so the difference is how they choose this safe edge to insert. Okay, so okay. But just to have an idea, what does it mean by safe edge? Okay. Now let's say that at the beginning, we're given this graph. Okay. Can you think of one edge to add to a minimal spanning tree, which you are sure that it would have to be in some minimal spanning tree? Can you think of such an edge that you know that this edge, well, cannot be wrong? It would be in some minimal spanning tree. Well, how about the edge with the minimal weight? Okay, so if this edge has the smallest weight, okay, intuitively, it has to be contained in some minimal spanning tree. In fact, if all the edge weights are different, then this edge must be in the minimal spanning tree. Okay, why? Because if you have a minimal spanning tree which didn't contain this edge, okay, that means that remember, I can use the similar argument. That means in that tree, this two endpoints were connected some other way, because this two endpoint has to be connected. There's a unique path connecting them. So the dotted line, let's say, is the tree path to connecting these two nodes in your minimal spanning tree. Okay, then I can do the same thing. I can just replace any edge here in this cycle with this edge, and my weight is only getting smaller because this one is the smallest weight, has the smallest weight. Okay, so intuitively, the safe the edge with the smallest weight is the safe edge to add at the beginning. Okay, all right. As I just said, today we're going to now talk about an algorithm called the Prim's algorithm, and next time we'll talk about a different gradient algorithm called Kraskow's algorithm. Okay, so the idea behind the Prim's algorithm is the following. Okay, let's say so. I'm going to use this slide because I need some space for drawing. Essentially, the Prim's algorithm is going to pick an arbitrary node to get at the beginning and start to grow the tree gradually. Okay, at any moment, what you would have is that at any moment you would see a partial tree already connected to some nodes. Okay, so we grow this tree, and then there's also all the other nodes outside not yet connected. Okay, and the Prim's algorithm will then at any stage would then find another edge that is safe to add and connect to one more node outside. Okay, and after that, now this is also connected. Then you continue this process till you reach all the other nodes outside. Okay, so it's on the high level. This sounds a little bit similar to when we compute the shortest path tree, right? So we start to grow a partial tree, and at any moment we reach another node, find the shortest path to it. Okay, here we just at any moment we're going to reach another node, which while maintaining that what I found so far is still a partial minimal spanning tree. Okay, so that's the idea behind the Prim's algorithm. Okay, so this is what I'm saying here. So we're going to incrementally grow a partial tree, connecting a subset of nodes S inside of V. Okay, so at any moment, all the nodes here are already connected. Okay, and then there's all the nodes outside, call them U, are not yet connected. Okay, and at each iteration, we're going to include one more vertex. U, where U come from outside. Let's say that we're going to reach this vertex U through some edge. And I'm going to call this edge a crossing edge. Okay, now what is a crossing edge? A crossing edge is simply an edge. So you already have a set of nodes, you already connected, and you have the nodes outside you have not connected. Okay, a crossing edge is any edge going from a node in S to a node outside S. Any such edge cross S and U is called a crossing edge. Okay, so a crossing edge is basically has one vertex in S and one vertex outside S. Okay, U is V minus S. U is basically all the nodes outside S. So a crossing edge is basically one vertex inside S, one vertex outside S. Okay, so every time I'm going to connect you at each iteration, I will connect, I will connect to a new node outside through a crossing edge. And the way that we're going to choose this new node is that I'm going to choose the crossing edge greedily. Okay, we're going to pick the crossing edge with the smallest weight. Okay, intuitively, why? Because that basically says that, okay, now I want to reach some node in U. What's the cheapest way to do so? In other words, what is the crossing edge with the smallest weight? Okay, so suppose this red one is the one with the smallest weight. then we're going to take, suppose this edge E has the smallest weight among all crossing edges. Then we're going to pick this node U and connect to it and add it to S and repeat. Okay, that's the algorithm. Okay, so this is a greedy algorithm because any moment I'm saying that I already have things already connected and things I haven't connected. Any moment I ask that, what is the cheapest way to grow my tree? By finding a crossing edge with the smallest weight. Okay, and I take that one. I grow the tree and I repeat. That's it. Okay, is the idea clear? All right, so let's just look at an example to make this more clear. But first, here is the high-level pseudo code. This is not really code. I mean, this is just giving the idea. It's a high-level outline. Okay, I'm using this form instead of using Python here just to make the structure more clear. Okay, so what we have, we basically at the beginning, U is the set of nodes outside. Okay, I don't represent S the set of nodes you ought to reach explicitly, but at the beginning, let's say that V1. So at the beginning, S only contains V1, just arbitrary, the first node, doesn't matter which one, okay? Then what you do is that at any moment, as long as the outside is still not yet empty, you pick so this is just the S, you pick the minimal weight crossing edge, that's it. Okay, this is just saying that I pick the minimal weight crossing edge and to reach a node Vj, and then now I set the Vj's parent to be Vi, and I take this Vj, now I can, so I already have S, and this is U. At any moment, I find the mean weight crossing edge, let's say this is Vi to Vj. Okay, so inside is already connected somehow, okay? So now I say that it shouldn't be parent, it should be predecessor, sorry, predecessor. So now that means that the predecessor of Vj is going to be Vi, so I set that to be Vi, and I now remove Vj from the outside, I include it, namely into S, that's it, okay? All right, so let's look at a concrete example to make this more clear. Let's say that at the beginning, my set S, which I'm going to mark here, okay? At the beginning, set S only includes V1, okay? So it's red. Everybody else at the beginning is outside, okay? What do? I say that, okay, let's now see what is the cheapest way for me to connect it to another outside node, okay? So I'm going to look at all the crossing edges. I have two crossing edges here. I have this edge going from inside S to outside. I have this one, okay? Remember that the inside is S and outside is U. Okay, so right now I have two blue edges. Those are my crossing edges, okay? Going from inside S to outside, and I pick the cheaper one. The cheaper one is this one. What does it mean? That means that we are going to now set V1 to be predecessor of V2, and I'm going to reach V2. So now my set S increase to be V1, V2, okay? And this is my S now, okay? So then next stage, I do the same. I say that who are the crossing edges now? Now my crossing edge are V1, V6, V2, V4, and V2, V3. Those are my crossing edges from inside to outside. Again, I pick the cheapest one. Now the cheapest one is this edge now. Okay, so I simply connect to V6. Okay, because this one has weight 3, while others have 5 and 7. Okay, so now I further increase to be also reach V6, and my S now will be, this is my set S, okay? So now when I add a new node, now I have more crossing edges. So edge V6, V4, oops, wrong color. So edge edge V6, V4, and edge V6, V7 now also crossing edges, okay? Again, I pick the cheapest one. Now the cheapest one is V6, V7, because that has a weight only 1. This has 4, 5, 7, okay? So now I also change my, also add V7, and this is my set S. Now note that so this is what we have now, okay? Then, and when I have this new one, I have new crossing edge. Now V4, V7 is also crossing edge. V7, V8 is also crossing edge. So the next cheapest one will be V7, V4, okay? So now I'm going to take V7, V4, and my set S will also include, so now this is V7, V4 is also, so this is my set S, and V4 is also in, okay? Note that now this is my S, this edge V2, V4, and V4, V6, they are no longer crossing because they're all connecting nodes, which is all the nodes we found. Let's make them red. So now these two blue edges, V2, V4, and V4, V6, they're no longer crossing anymore, okay? The new crossing edges still is, I now have this as my crossing edges, okay? So repeat, the next edges we're going to take is V7, V8, because 4 is the smallest weight, okay? And that would change the, so we're going to add V8 next, and this would make our set S like this, and we have new crossing edges. And the next cheapest one will be the cheapest among 9, 6, 5, 7. So the cheapest is edge V4, V5. So I add this one, reach V5, and our set S now becomes this. And because of this, the edge V5, V8 is not crossing anymore, okay? But we have new crossing edges, oops. V5, V3, and V5, V9, okay? So we continue this process, and I'm just going to go a bit faster, and we will next reach the cheapest, the next one is V2, V3, and then in the end we go V3, V9. So this is our final spanning tree. All the edges are the spanning tree edges, okay? And this point, outside become empty, we're done with the algorithm, okay? Questions? Okay, all right. So this is just the set of red edges we saw just now. I marked them again. Okay, you can repeat the process of solving as an exercise later. Okay, all right. So why is this algorithm correct? Okay, so here again, I just want to show you some intuition. Okay, you don't have to know the details, but I hope you get the intuitive idea why this algorithm works. Okay, so similar to shortest path, the way that we argue that the algorithm is correct is through looking at the loop invariant. Okay, essentially the loop invariant here is basically this MST theorem, which is basically we say that suppose the loop invariant we maintain is that at any moment the partial tree we already have is a subtree of some minimal spanning tree. Namely, so far we haven't made any mistakes yet. Okay, and this MST theorem basically says that, okay, if you already have a subtree of a minimal spanning tree, okay, and then now you pick this minimal weight crossing edges, okay, so you pick this crossing edge gray delay, okay, then the union of them must be a subtree of minimal spanning tree still. So this guarantees that we can maintain the loop invariant because this is E is exactly what our algorithm will take. Okay, in other words, the theorem is saying that if you have loop invariant at one iteration, okay, so you already got a partial tree of some minimal spanning tree, then by choosing the crossing edge gray delay to connect to another outside nodes, afterwards, this tree with this new crossing edge is still a subtree of a minimal spanning tree, namely the loop invariant is still maintained. Okay, so If we can prove this theorem, then clearly the algorithm is correct, because at any moment we always maintain a correct partial minimum spanning tree till in the end we reach all the nodes. What we have is a minimum spanning tree. Okay, so all we need to do is to prove this MST theorem. Okay, so intuitively, why is that correct? Well, intuitively, let's say that suppose at this point we already have some partial tree. So this is our set S. I already have some partial tree. Okay, so this is our partial tree. And remember that the MST the algorithm we described, the Prim's algorithm, will pick the min weight crossing edges. Let E be that min weight crossing edge. Okay, and our goal is to show that the T union E is still our goal is to show T union E is still part of a minimal spanning tree. Namely, we didn't add any bad edge. It's a safe edge to add. Okay, so that's what we want to show. Okay, I'm not showing you, so there are more edges outside, more nodes outside, and I'm also not showing you all the other edges. Okay, so the proof is that let's call this one UV. Okay, so let's say that suppose this is not the case. Suppose T union E is not in the minimal spanning tree anymore, but I know that the T was part of some minimal spanning tree. Okay, call that tree A. Okay, so there was some minimal spanning tree contains T, but let's say there's no minimal spanning tree contains both T and the E. Okay, that means that in that minimal spanning tree, okay, we have there must have been, when I add E to that minimal spanning tree A, there must be a path connecting U to V. Okay, let's say that the path connecting U to V, I'm just doing something. Because I mean, in the minimal spanning tree, U and V has to be connected, right? There's a unique path between them, okay? And this path has to go from inside the set S to outside. So if you follow this path, first this path is probably in the tree. At some point, it has to leave the set S. In other words, I have to see a crossing edge at some point along this path. Okay, call this one E prime. Okay, now since what I can do is that I can simply remove E prime and then put E into replace it by E. Okay, because E has the smallest weight among all crossing edges. Doing this can only reduce the total cost, right? Okay, but by doing this, I get another spanning tree. That means that I can, if E has the same weight as E prime, then I can simply remove E prime and add E there. Then I got another spanning tree has the same weight, which has to be the minimum. Okay, if E is smaller than the weight than the E prime, then that's a contradiction because it's not possible. Because I mean, how can I get a tree with a smaller total weight? Okay, because the original tree A has to be the minimum spanning tree. So that's not possible. In either case, this means that E, T, and E must already be in part of a minimal spanning tree. Okay? So again, the idea is that T was in the minimal spanning tree, and let's call that tree A. Okay? Suppose E is not in A anymore. Okay? When you add this minimal crossing edge, minimal weight crossing edge, if this minimal weight crossing edge, E is not in the spanning tree, that must mean that in the spanning tree A, minimal spanning tree A, I have a way to connect the two endpoints of E. Okay, but that path connecting them has to have a crossing edge at some point, right? And I could remove that crossing edge and replace it by E, and I still have a spanning tree, but this spanning tree, the weight can only be smaller. Okay, so either it's a contradiction or I find a spanning tree of the same weight. So in either case, E must be in the minimal spanning tree. Okay, so that's the idea. Okay, all right. So I put down the argument here, which is what we just said. Okay, the A is the original minimum spanning tree containing T, and if E is not in that, it's not an edge of this minimum spanning tree, then we must form a cycle, okay? And that means that the two endpoints of E has to be connected by an edge, and then we can find another edge which is crossing, and so on. Okay, all right.